Hello. I hope you did well on that first exam and that you're ready to move on to the next section of material. We're going to be picking up with Chapter 14 today, and Chapter 14 deals with something called statistical process control. It's kind of a difficult sounding topic, but it's not really that difficult, and in fact, all it really is an application of what you already know, which is hypothesis testing. It's an area which is very important right now in the business world. It's used quite heavily, and it's a real marketable skill. So if you really understand how to do this, it's something you can put on your resume and something that you can help someone else do, or at least understand what someone else does, or maybe do it yourself. So, statistical applications in quality and productivity management. Some portions of this chapter I won't cover quite as much because you'll see them in other classes, but the control charting process is what I want you to be aware of, how to do that and how to interpret the meaning of those. So let me explain before we get much further what is the objective of what we're doing in this chapter. The basic objective is to maintain consistent high quality. To do that in terms of a marketing effort, to do that in terms of servicing your customers, and do that in terms of providing a product that the quality is consistently good rather than sometimes good and sometimes bad. Well, how do we know whether that's going to happen or not? What we have to do is we have to monitor the process on a continual basis to make sure that things are operating the way they're supposed to operate. Whenever we use control charting, we also make the assumption the process is operating normally, the normal distribution assumption that we've been using so far. So if we see unusual values, or what we call outliers, or values that are a lot different from what we would expect to find, then we say, maybe there's a problem here. Maybe things are not working the way they're supposed to work, and therefore we might need to take action to fix things. Okay, so again, we're going to be doing some control charting in order to tell you how to monitor that process. And a key thing you want to focus on is which control chart should I use for a particular type of data. Because on your next exam, I probably won't say use a P chart or use an X bar and R chart. I'll say here's the data, use a control chart to tell me whether the process is in control and whether you notice any trend or not. Okay, so let's see how this is going to work. The main thing we're going to focus on is on the right side of this page right here, Tools for Quality Improvement. P charts, R charts, and X bar charts. Okay? And we're using these to find out, are we really operating in control, or do we have any problems that we need to fix? Okay? I'm going to skip a few slides here. Yeah, I'm going to go to this next slide, which is slide 11, and this has to do with the theory of control charts. The process, which is what we're examining, is a repeatable series of steps leading to a specific goal. It might be the production of something, it might be servicing the client, whatever it is we're trying to do. So we want to examine that process, which is done on a regular basis, to find out how well it's meeting the goal that we're trying to accomplish. The control chart then is used to monitor the variation that exists in the measured value in the process. So how much is it changing? We expect some variation, but we don't expect a lot of variation. Any process is always going to have what we call inherent variation. That is natural or normal variation, which is always going to be there. We might be able to reduce it a little bit, but we're never going to be able to eliminate it. So when we're doing our control charting, we're trying to figure out, is this variation that we see built into the system or inherent, or does it indicate a problem, something we need to work on or do something about? Okay, so there's basically two categories or two types of explanations we have for variation in values. First is called special or assignable cause variation, and the second is called chance or common cause variation. The one that's always going to be there is the chance or common cause variation. It's built into the system, it's random, and there's a lot of reasons why it occurs, but we're not likely to be able to eliminate it. It has to do with things like, some days people come in more alert than others. Some days they feel fresh. Some days the temperature in the building might be better than others. There's a lot of things that could go in there. The machine might be operating better sometimes than others. But if it's a particular problem, it's something that isn't normally the case, that's what we want to know about. That's called special or assignable cause variation. These are fluctuations that are not part of the system, but they're actually problems that may need to be corrected. And they are noticed by data that is outside of the control limit or a trend that we notice occurring. And we'll define both of those in a minute so you know what we mean by that. If all the data is in control and there's no trend, then all the variation is due to chance or common cause variation, is our assumption. If we have data outside of the control limits or a trend, that may indicate special or assignable cause variation. Okay, so here's the way we do it. We take the variation or the difference in the values that we observe and we say common cause plus special cause has to equal total process variation. The common cause, we're not too worried about it. That's the part that's built into the system, and no two products or service experiences are exactly the same, so there's going to be a lot of variation that's going to occur. The one we care about is special cause, but common plus special cause has to equal total. That's the identity that we're working with. All right, these are examples of sources of variation. People, machines, materials, methods, measurement, environment. Any of those things can cause variation. Common cause variation is naturally occurring and expected and the result of normal variation in materials, tools, machines, operators, and the environment. So these are things that are always going to be there. We can't do anything about it. The ones we care about are the special cause variation. Abnormal, unexpected variation. There is some reason why it's occurred, and it's beyond what we would assume to be normal for the process. Okay, so how are we going to measure these things? We're going to use what are called control limits. And we're going to have an upper limit and a lower limit. If the values exceed the control limits, then that tells me I have an out of control process. Notice the way that the diagram is drawn here. There's a center line, and then there's an upper and lower limit, which is 3 standard deviations in either direction away from the process mean or average. Okay? Now, where does the 3 standard deviations come from? It comes from the empirical rule. We assume the process is normal. So therefore, our null hypothesis is really the process is operating normally, and the alternative is that it's not operating normally. So if we get values more than 3 standard deviations, those are called outliers. The probability of that happening with a normal distribution is only 0.2%. Because remember, within 3 standard deviations, I would expect 99.8% of the values based on the empirical rule. So, are there any values above the upper or lower limits? That would cause, even if one value is outside the limits, we have an out of control process. Okay? So we've got to come up with an average and then find out what is 3 standard deviations in either direction. That's going to be my upper and lower limits. All right? Common cause variation occurs within what is the shaded pink part here, and unexpected or special cause, assignable cause variation occurs in the blue area, which is outside of the control limits. Okay, if this is what our data looks like when we graph it, we always have time on the x-axis, and we have whatever the other variable is that we're trying to look at. We want to know, are all the data in the pink area, or the upper and lower control limit region, or do we have any values above or below those limits? If we have a value like the red dot up here, which is in the blue area, that says the process is out of control. We have some special cause variation because these values are more than 3 standard deviations in either direction away from the average. That's what we're looking for. Okay? So, how do we use the control chart? Here it is. We're checking for 2 things basically. Is the process in control, and are there any trends? So the null hypothesis says the process is in control. The only variation that exists is common cause variation, which we can't eliminate. The alternative is the process is out of control. We only have special cause variation. So if it's out of control, That's when we need to fix things, try to figure out what the special cause variation is and eliminate it, then go back and check the process again to see whether we were successful in eliminating the special cause variation. Okay, if I have an in-control process, that says there's no out-of-control points. Everything is within the 3 sigma limits. As long as the common cause variation is small, then we can continue to monitor the process. Even if it's within the limits, if there's a lot of variation, you might want to try to reduce that variation a little bit. Might be difficult, but it would be helpful probably if you could do that. But as long as all the data points are within the limits, then we say the process is in control. If we find 1 or more points outside of the control limits, the process is out of control, which means we need to try to fix it, see what's going on there. If we have 8 or more points in a row, that's defined as a trend. A trend can take several different forms. If I have 8 or more points above or below the average, that would be a trend. Or if I have 8 or more points going up or going down, that would be an average. They have to be consecutive or in order points because we're looking at things over time. The reason we care about these trends is because if they continue, they're likely to cause an out-of-control reading. They're likely to cause a problem in the future, even though they might not be there yet. The average would be going up or going down, or something happened to cause it to go lower than it was before or greater than it was before, and we want to find out what that something is. Anytime we have 1 or more points outside the limits, it's out of control. 8 or more points in a row would be a trend. So you count here, 1, 2, 3, 4, 5, 6, 7, 8 points below the average. That's why that one indicates a trend. Here, they're not below the average, but they're all going up, 8 in a row. So therefore, we have a trend again. So those are the 2 things we're going to be looking for. Is the process in control? Is there any trend? Those are the 2 questions. When we have out of control conditions, 1 point or more outside or a trend, we have both common cause and special cause. We've got to figure out what the special cause variation is and fix it. If it's a good thing, we want to build it into the system. If it's a bad thing, we want to remove it. So sometimes this out of control thing might be good. We just have to figure out, is it helpful or harmful, and then take appropriate action. Okay, here's the 2 types of control charts that we have. P charts, X bar and R charts. The main way you're going to recognize these, I'll give you a few hints. One is the type of data. A P chart is used with attribute data. We're talking about proportions or percentages. You could also use the word nominal data here, which we've used before. Nominal and attribute mean the same thing. Attribute means it has some characteristic or it doesn't. Okay? The X bar and R charts, we're going to be dealing with sample means and ranges. So now we're talking about interval or ratio data, which is also called numeric data. One other way to distinguish between these, the P chart is always going to have large sample sizes. When I say large, I mean hundreds or even thousands in each observation period. When I talk about X bar and R, these are going to be small sample sizes, like maybe 3 or 5 or 10 at the most in each of the samples that I'm going to take. So small samples, X bar and R, large samples, P chart. Some other helpful things, conceptual questions. Remember, when I say conceptual questions, that means it could be the subject of multiple choice questions on your exam. You're getting a better idea of what I like to do there, so kind of pay attention when I say conceptual questions. When I talk about P charts, remember P is a proportion or a percentage. The minimum value for a P chart is 0. Maximum value is 1. So if I get a value above 1, I know I've got a mistake. A P chart cannot have a negative value because it is a percentage. An X bar chart can have a negative value. I can have an average which is negative if all the values are negative, or a lot of them are. I can have a negative mean or average. I can't have a negative range because a range is largest minus smallest value. So even if all the values are the same, the range would equal 0. It's not going to be negative. Okay, so remember, both R and P cannot be negative. Only X bar can be negative. Okay? So those are some helpful hints to help us to recognize which chart is which. So we're going to start out then with the P chart. P chart talks about proportions, nominal data, or attributes. So for example, if we're looking at computer chips, we might be saying, what percent of the chips that we produced are defective? And divide by the total number of chips, that's going to give me the proportion of defective chips. Either they are defective or they're not. There's only two categories, so that's why it's going to be a proportion. And success we're going to define as the characteristic of being defective. So X divided by N will tell me the percentage of chips that are defective. We can have equal or unequal sample sizes whenever we develop our subgroups. However, the unequal sizes, if we have those, should not differ by more than 25% from the average. And it is a little easier to develop with equal sample sizes, so we tend to try to be equal if we can. In order to do the P chart, again, we have to have approximately normal distributions here. So N times P, N times 1 minus P, both of those products have to be at least 5 to do our P chart. Okay, here's how we do it. First thing we do, if they're not already given, is we calculate the subgroup proportions. Then we graph them. Then we compute the average proportion, or what's called P bar, and then we come up with the upper and lower control limits, put in our center line, and then graph the data to see whether we have any out of control points or not. So here's an example. We'll look at another example in a minute. We have subgroups. These are the observations that we took on each of these several days or time periods. We had 150 in each sample. Notice that's pretty large. That's going to tell me it's a P chart. It's not a real small sample size. It's pretty big, 150 in each group. And out of that 150, how many of them were successes? 15, 12, 17, etc. So to find my sample proportions for each of those subgroups, all I do is take number of successes and divide by the sample size. 10%, 8%, 11.33 for those. To find P bar, which is going to be my average subgroup proportion or my center line, I just add up the sample proportions and divide by the number of subgroups that I have. Okay, now we're going to look at the formulas. These formulas look pretty difficult, and they can be, because you can get confused as to what they mean. Here's two ways to find P bar, which is going to be the center line of my P chart. First thing is, I can just sum the P's, which is the proportions, if I already have sample proportions, and divide by the number of subgroups of size N, or the number of time periods on which I took samples, you could call it that. Number of subgroups is K. So you need to remember, K is the number of periods on which I took observations. P is the sample proportion for each of those subgroups. So if I add those proportions and divide by the number of periods, that's going to give me the average proportion. Alternatively, especially if I have unequal sample sizes, I can add up the number of defective things, non-conforming items, whatever they are, that's X, add those up and divide by the sum of N, which is the total number of items sampled in K samples. So if I have 150 in each group and I've got 3 groups, I'd have to multiply 150 times 3 to find this denominator. Okay, here's how I find my control limits. P bar times 1 minus P bar over N bar, the square root of the whole thing. Okay, so N bar is the number of observations in each group. You want to remember that. It's not the number of groups or the number of days that I took observations. It's the average number in each group. If that's 150 every day, then N bar equals 150. If it varies a little bit, I've got to calculate that. P bar is going to be the average of those sample proportions. And then 1 minus P bar is the other value. Okay? Now here's our formula. This will be on your formula sheet. For the upper limit, it's P bar, the center line, plus or minus 3 times the square root of P bar times 1 minus P bar divided by N bar. 3 is a constant. That's 3 standard deviations. So don't worry about that 3, just put it in there. Here I've got minus 3 because this is the lower limit instead of the upper limit. Okay? Proportions are never negative, remember? So if I find a lower limit that would be negative, what I do is I set it equal to 0 or equal to the x-axis on my graph. Because I can't have a negative value, I don't have to worry about it below 0 anyway. Okay, here's an example. This is a P chart. You are the manager of a 500-room hotel. You want to achieve the highest level of service. 7 days, you collect data on 200 rooms each of those 7 days. The question is the process in control? So let's make sure we know what's going on here. We have a sample of size 200 every day, that's N, and we have 7 days, which is K, that is the number of periods on which we're going to take observations. So we've really examined 1,400 rooms. 200 times 7 is 1,400 rooms on those 7 days. We had 500 rooms in the hotel, but we only examined 200 of them each day, not all 500. But what we want to know is the process in control? So here's what the data looks like. We've got 7 days, that's K. Then we've got the number of observations each period, that's N. So N bar is going to be 200 because we had 200 rooms every day. To figure out the sample proportions, what I do is I take the number not ready, or the number with the characteristic, which is X, and I divide by N, which is the number of rooms. 16 over 200 is 8%. 7 over 200 is 3.5%, etc. So these are my sample proportions for each of the 7 subgroups that I've now calculated. Okay, we're ready to set up our control chart now. So what we want to do is to find P bar, that is the average proportion. The way I do that is I sum my x's, which is the number of values that have the characteristic. So we can go back to the other page just a second so you can see where this number is coming from. Okay, this is the number of rooms not ready. Add up those values, and the total number of rooms would be 200 per day times 7 days. So that's what we did over here. We got 121, which is the sum of the x's, 1,400, which is 200 times 7. It's 1,400, or just add up the 200s. So that gives me 0.0864. That is 8.64%. That's my average. That's my center line of the control chart, or my P bar. To find N bar, I just take the number of observations on each day, which is 200, add them together, and divide by 7, which is the number of days on which I took observations. So I would get 200 for N bar. That's pretty obvious in this case because they're all the same. But if they're not, you still use the same process, and you come up with the average N. Now I go to my upper and lower limits. P bar, 0.0864. 3 is a constant. That means 3 standard deviations. And P bar is still the same. 1 minus that. N bar, remember, is 200. So I plug that in. My upper and lower limits are 0.1460 and 0.0268. That means 14.6% to 0.68%. I write them as a decimal, but that's what they really mean. If I get values above 0.146 or below 0.0268, I would reject the null. Remember if, which means the process is out of control. If I find values, if the lower limit turned out to be negative, remember, I've got to set it equal to 0. In this case, it's positive, so I can use that number. So this is my graph. Now what I've done here is we've put the center line, 0.0864 in the middle, that's the blue line, the upper and lower limits, 0.146, 0.0268, and then what I'm going to do is plot the sample proportion values. And you've got to do them in order. Day 1, 2, 3, 4, 5, 6, 7. All the values are within the control limits, and there aren't 8 points above or below the line or going up or down. So this is what I would conclude. Individual points are distributed around P bar without any pattern. The process is in control, no values above or below the limits, and therefore, if we can reduce common cause variation, that'd be okay, but there's no obvious problem which is due to assignable cause or special cause variation, and there's no trend in the data because it's not going up or down 8 points in a row or above or below the average. Okay, so there's an example. Now we're going to give you another example problem to work from the chapter. And we're going to be in the section of the chapter which is 14.4. And what I want to do here is kind of work through one of these with you, and then we'll give you some more problems to work on your own. And let's see, which problem do I want to work here? We're going to work problem 14.6, which is page 517. Okay, so let's read our problem and figure out how we're going to do this. We have the bottling division of Sweet Susie's Sugarless Cola maintains daily records of the occurrences of unacceptable cans flowing from the filling and sealing machine. The following table lists the number of cans filled and the number of non-conforming cans for 1 month, based on a 5-day work week. Okay, so this data is actually found on the data disk in the back of your book. You can call it up that way, col.aspc, or you can type in the data like this if you want to. Our objective on the next page is to construct a P-chart for the proportion of unacceptable cans for the month. Do we have an out-of-control signal? And if we have a problem, what can we do about it is basically what it's asking me. Now, when I give you a problem, it probably won't say construct a P-chart. It'll say do a control chart for this data. So let's see how we would figure out that this is a P-chart problem. It's talking about unacceptable cans. So when I produce these cans, they're either acceptable or unacceptable. So that tells me I only have 2 categories. It sounds like a percentage. Okay? So I have a different number of observations on each day. I've got 22 days. So let me write down a little bit of what I know here. K, which is the number of periods on which I'm going to take observations, is 22. Okay, that is 22 days that I'm going to gather my data. Now I've got to find n bar. Okay, to find n bar, the reason I have to find n bar is because I didn't have the same number of cans on each day. So what I've got to do is add up the 22 values there, 5043, 4852, etc., 22 numbers, add them all up and divide by 22. So that means sum the x's and then divide by k. Okay, that's going to give me what we're going to call n bar. So this is problem 14.6. You can do that yourself, work it out, see what you come up with. I will give you the correct answer here in a second. 14.6. I'm going to need that in order to do my formula, so that's why I'm trying to calculate n bar. 5152 is approximately that value. 5152. Okay, so that's my n bar. That's the average number of cans on the 22 days that I came up with. What I did, again, remember, is add up the number of cans filled and divide by 22, which is K, number of days on which I took observations. All right? Now, some other things I'm going to need to calculate. I'm going to have to calculate P bar. That's my average proportion. So to find that, I can take all my unacceptable cans and add them up. Okay, whatever that number is going to be my numerator. So I'm going to call that the sum of x. And then I'm going to divide that number by, I messed up here. Whoops. This is going to be the sum of n, not the sum of x over here. That is the sum of the number of cans that we had on each of those 22 days. Sum the n's and then divide by k will give me n bar. Here we're going to sum the x's, which is the number of unacceptable cans, and divide by the total number of unacceptable cans. So what is that going to be? The denominator there is going to be n bar times the number of days on which I took observations, which is k, 22. So I'm going to take 5152 times 22. That'll give me my denominator, and then my numerator is going to be the sum of the unacceptable cans. So that value, P bar, for this problem is equal to 0.01288. Okay? 0.01288. So that is about 1.29%. Something like that is what P bar is. On average, 1.29%. Okay, now I've got everything I need in order to construct my control chart. What I'm going to do is I'm going to make a table here. Along the x-axis, I'm going to have 22 days. I'll go through this at least enough that you have a pretty good idea of what's going on. Here's day 1, starts over here. All right, I'm going to put down my average, P bar, which equals 0.1288. And then I'm going to have 3 sigma limits in either direction around that value. Remember, the formula says that what I need to do is to take, the formula is found on page 512 in your book. I'm going to take 3 times the square root of P bar times 1 minus P bar over N bar to find the value that determines my upper and lower limits. Okay, when I work out those limits, what I should come up with is 0.00817 as my lower limit, 0.00817, that's my lower control limit, and my upper control limit, which is going to be up here at the top, whoops, that's UCL, we'll call that one, equals. And now what I'm doing is I'm adding and subtracting 3 standard deviations to 0.1288, and I'm going to get 0.01288. So this is, there we go, 0.01, which means about 1.288%. So I've got 0.8% here. My upper control limit is 0.01759. Okay, so it's about 1.7, 1.8%. 0.8% is my lower limit. And now what I've got to do is go through and plot each of the data points that I've got. Before I do that, though, I'm going to have to find out what these sample proportions are for each of those 22 samples. So I've got to take unacceptable cans, 47, divide by the number of cans filled on that day, 5043, which gives me the actual data or the sample proportion for day number 1. I go through and plot that data for every one of those days, and what I should find is that on day 4, I'm going to have a value which is just below the limit over here, about here. Okay, all the other data should be, I'm just kind of roughly drawing this now, but it should be kind of going down. This is the only day below the limit. Then I go up quite a bit after that, and then I go down a little bit. This is about what your data should look like. And then it begins to go up and down sort of randomly most of the rest of the way, like that. So this data point is the one that concerns me. On day 4, so this is the way I'll write it up. Day 4, I have an out of control point. That means there's some assignable cause here. There's something going on day 4. The process is out of control. So in terms of my null hypothesis, remember the null says process in control. The alternative says process not in control. Okay, so what I've decided is because of day 4, the process is not in control. There is a problem because I had one data point which is outside of the lower control limit. And is there any pattern in the data? Well, what we find is, I didn't draw this quite as well as I should have. If I did it correctly, we would have data points that are going up, but they're all above the average. So we would say process is not in control because of day 4, and we have a trend, an upward trend. The last 8 points are all above the average. So therefore, we've got a problem. We need to fix things. This process is not operating the way it should be. We need to figure out what happened on day 4, and we need to and maybe try to build that into the system because that was pretty good. But it looks like things are getting worse from here on out because the average is going up. So we need to fix things before they continue to get worse. We might even get points outside of the control limits up there on the other end. So that's how this kind of control charting works. We'll give you some more problems to practice on your own.